We can go ahead and start. I'm really pleased to have Michelle Mastrianni here to give us a talk on discrepancy theory. And just as a quick bio, Michelle is a fifth-year PhD candidate at the University of Minnesota and is advised by Dmitry Billig. Yeah, Michelle, take it away. Thanks so much.
Thank you. Thank you so much for inviting me. Yeah, I'm going to talk about some problems in discrepancy theory today. So I'll start with a bit of an intro to that. And yeah, let's get started. So if you haven't heard of discrepancy before, it's the whole notion of discrepancy theory is about approximating continuous objects via discrete distributions. And in this talk, we're going to be working with finite point sets P of size n, and the discrepancy is a way to essentially measure how well distributed such a point set is in some space. So you could be in the unit cube or on the sphere. In this talk, we'll be focused on the unit cube and specifically in 2 dimensions. But the discrepancy can be measured with respect to some class of sets, some natural class of sets. So you could take axis parallel boxes, balls, half planes, etc. So that's your script A is the class of sets. And for a particular set A in this class of sets script A, so if I'm taking axis parallel boxes, if I want to measure the local discrepancy of the point set P with respect to one particular box A, then this is measured as the deviation between the expected number of points in that box, which is given by n times the volume of the box, because we're in the unit cube, and the actual number of points in the box. So it's a deviation between the expected and actual behavior of the point set. And then if we talk about the L infinity discrepancy of the point set with respect to the entire class of sets, now you're looking at a supremum of these local discrepancies. So in some sense, you're looking for like the worst possible deviation in your entire class of sets. And the discrepancy function with respect to the class of sets script A is a function of the number of points n, and it looks at over all point sets P of that size n. It takes an infimum of these discrepancies of the point sets. So you're looking for kind of, in some sense, the best behaved point set of that size. So where you're trying to minimize these local deviations among all sets in your class of sets, script A. So that's the discrepancy with respect to a class of sets, and we're interested in bounds on this discrepancy function, or like asymptotics, as the number of points n grows. Okay, so as I mentioned, one of the most natural classes of sets with respect to which we can study the discrepancy in the unit cube are axis parallel boxes. So I'll denote that script R sub D in D dimensions. And it's often easier, which you'll see why in a second, to study the class of corners, which are essentially just anchored boxes at the origin. And if you don't care about the constant which depends on the dimension, discrepancy bounds with respect to corners are roughly, they're of the same order in terms of n as discrepancy bounds with respect to axis parallel boxes. So if you're only interested in asymptotics in n, this is sometimes an easier class to work with. So in 2 dimensions, the order of the discrepancy is entirely understood, and the discrepancy with respect to corners, or all rectangles really, is logarithmic. It's log n. So for an upper bound for discrepancy, we can come up, if we have a specific point set that satisfies a particular upper bound, that suffices, because in the definition of discrepancy, we're looking at a supremum over, or sorry, an infimum over point sets. So for an upper bound, we just need to show there exists a particular point set with that upper bound. For lower bounds, we need lower bounds to hold for all point sets. So for an upper bound, we have specific constructions that achieve logarithmic discrepancy. And for lower bounds, we can use orthogonal function methods, which I'll get into a little bit more in a second. So one just note on why corners or axis parallel boxes are particularly natural classes of sets is that you have these inequalities for numerical integration errors. So particularly one of the most well-known ones is the Koch-Smolowka inequality, which gives an error bound on the discrete approximation of an integral using points in some point set, and that bound is in terms of the discrepancy of the point set with respect to corners. And then you also have this piece that is dependent on the function itself. It's the variation in the sense of Hardy and Krauss. It's roughly the L1 norm of the mixed derivative. But in any case, so this is a very natural way of relating kind of the continuous integral to a discrete approximation in terms of the distribution properties of the point set P. Okay, so I mentioned that for lower bounds, we can use orthogonal functions to get orthogonal function methods to get lower bounds on the discrepancy. And the way that this is done is actually by using an L2 average of the discrepancy. So in the discrepancy of a point set, we're taking a supremum over all sets in our class of sets. But if instead we take a particular average, so for corners, there's a really natural way of doing this because, for example, in the unit square, each point X defines a corner C sub X. And so we can basically integrate the local discrepancies of the point sets with respect to these corners over the unit cube and take this L2 average. And then exploit orthogonal function techniques to get a lower bound of square root of log. And this was later improved to log of n using other methods. So in 2 dimensions, the discrepancy is completely understood. We have logarithmic discrepancy with respect to corners. In higher dimensions, this is probably the most like intriguing open problem in all of discrepancy theory is what the precise order of the log is in higher dimensions with respect to axis parallel boxes. So there's kind of 2 schools of thought. The first conjecture is that the true discrepancy is log to the d-1. So you kind of gain a log in every dimension. And the reason for this is that there already are known explicit constructions of point sets which achieve this discrepancy. And they're kind of higher dimensional generalizations of very classical examples of 2-dimensional point sets with logarithmic discrepancy. So we already have these explicit constructions. So this is one school of thought. The other school of thought is that potentially the correct order is d/2. And this is motivated by connections to other areas of harmonic analysis. So the orthogonal function techniques that are used to prove lower bounds in discrepancy theory, there's a lot of similarities between those proof techniques and proof techniques in, for example, like the small ball inequality. And in those cases, you have this d/2 popping out. So just on a heuristic level, this is what motivates kind of a second school of thought. And this is definitely by far probably the biggest open problem in discrepancy theory as a whole. And just a note that the lower bound, or the best possible lower bound as up to now, is this d-1/2 and then plus like a small constant depending on the dimension. And that improvement by some epsilon depending on the dimension was done by my advisor Dmitry Bilik as well as Michael Lacey. So yeah, okay. So for the rest of the talk, we're going to restrict ourselves to 2 dimensions and study the discrepancy with respect to essentially rotated rectangles in the plane. So we're concerned with classes of sets that consist of rotated rectangles. And the discrepancy with respect to the class of all arbitrarily rotated rectangles is also well studied. So up to now, we've discussed just rotations in one direction. So just the axis parallel case, that's completely known logarithmic discrepancy. If you allow for arbitrary rotations, then this is also well studied, and there's just this potential open problem of trying to remove a square root of log, or and it's unclear whether this is possible. But the lower bound is n to the 1/4. The upper bound has this extra square root of log. So we have polynomial discrepancy once we allow for all arbitrary rotations. The upper bound is shown via a probabilistic method called jittered sampling. I'll go through the proof briefly because it's interesting and nice. So for the upper bound, we don't actually have an explicit deterministic point set which achieves this discrepancy. We only have we can only show existence. So we don't know what this point set looks like that achieves this discrepancy, but we at least have existence. And for the lower bound, again, we use L2 methods, so we can achieve a lower bound on the L infinity discrepancy by achieving an lower bound on the L2 average. And the results also extends to higher dimensions. So here the power is 1/2 minus 1/2d instead. And the same bounds also hold for balls in D dimensions, and also spherical caps on the sphere. Okay, so this is kind of the setting that we'll be working with. We have an allowed set of rotations, omega, and then let script r sub omega be the class of rectangles that make angle theta with the x-axis, where theta lives in that allowed rotation set. So it's all rectangles rotated by something in that allowed set. And we've already discussed the case when omega is a singleton, we have logarithmic discrepancy. And then if you allow for all rotations, we have polynomial discrepancy. So our question, our kind of fundamental question in the rest of this talk, is what happens in between these 2 extreme cases. If you allow for more rotations than a single rotation, but you still restrict the set of rotations in some sense, what happens? What's the correct order of the discrepancy? Okay, so in order to talk about this, I need to say a brief note on Diophantine properties of rotation angles. So in the axis parallel case, when we just have a single rotation, so axis parallel boxes, one of the standard ways to generate a low discrepancy point set, so a point set with logarithmic discrepancy, is by taking a standard lattice and rotating it by some angle with good numerical properties in some sense, and rescaling it appropriately, and that produces a good low discrepancy point set. Just a note that in the unit square, the standard lattice doesn't do very well with respect to discrepancy, because you have these, you can take like an axis parallel rectangle that looks like that. This has volume 1/square root of n roughly. And then in the definition of discrepancy, if you multiply n times the volume, you get a square root of n, and there's no points in there. So you get square root of n discrepancy. So that's bad, because we know that you can get down to logarithmic discrepancy in the case of axis parallel rectangles. But yeah, if you take some angle that is where the tangent is badly approximable, so in some sense it's far away from every rational number, then the resulting lattice is going to have low discrepancy. And the kind of heuristic explanation of that is that these axis parallel boxes are going to kind of miss the lattice at all the right places. So, and in general, the discrepancy of these rotated lattices depend on kind of how badly approximable that tangent is. So the resulting power of the log is going to depend on those numerical approximation properties. And just a note that if you have a finite set of rotations, you can find, it's possible to find some angle alpha that is essentially badly approximable with respect to every angle in your finite set of rotations. And so you can also get logarithmic discrepancy in that case as well. The constant might differ, but it is possible to find an angle that's like simultaneously badly approximable to everything in your allowed rotation set if you have a finite set of rotations. Okay, so what about other sets? So far, kind of the only sets that have been studied are given in the following paper from 2016, and the goal here was to get upper bounds on the discrepancy. And they made use of these numerical approximation properties. So kind of extending the idea for finite sets of rotations, and instead studying like particular infinite sequences. And so these are kind of, this is the summary of the discrepancy results from that paper. And the thing to note here is really that, okay, like when you have, so for example, a Lacunary set, it's kind of like a sum of several Lacunary sequences. So that's a denser set than just a single Lacunary sequence. And the discrepancy, the power is going to be larger in that case. So the denser the set, the larger the discrepancy. This makes sense. For super Lacunary sequences, which are Lacunary sequences which decay super exponentially, this is much sparser than a Lacunary sequence. So you get something even better. And then they also were able to get a result for sets of positive upper Minkowski dimension. This result is really only useful if D is less than 1/3, because in that case, the power is 1/4. And already for all directions, we had that upper bound of n to the 1/4 times the square root of log. So, so this is really only useful when D is between 0 and 1/3. But in any case, this is kind of the summary of results so far for these intermediate cases of rotations, and they're all upper bounds, and they all make use of these Diophantine properties and sort of covering lemmas for the sets. Okay, so turning back to the case of all rotations, I want to just go through the upper and lower bounds, and then in the remaining part of the talk, I'm going to discuss recent results obtaining a lower bound for the case of a restricted interval of rotations. But in order to do that, I want to first go through this all rotations case to kind of show you why the techniques for obtaining lower bounds in that setting don't fully translate once you restrict the allowed set of rotations to an interval. Let's first discuss the upper bound though. So this, I mentioned, I just want to go through this because I think it's a nice proof. And it also kind of shows where this square root of log n pops out. So the idea is that you use jittered sampling methods, which essentially are, this is a way to kind of randomize a point set, but also introduce a little bit of extra structure. So if you take an equal area partition of the square, so you can just take a grid in this case, but any equal area partition will do, then the construction is that you pick a point uniformly at random in each grid square. So this introduces some extra uniformity just by virtue of having this equal area partition. And then for an arbitrary rectangle in your class of rotated rectangles and grid square in your set of squares, you define these random variables, which essentially keep track of the local discrepancy with respect to the set R intersected with that grid square. So, for example, you might be interested in the local discrepancy of just this little piece. Okay, I didn't fully shade it in a nice fashion, but you know what I mean. So then if you're interested in looking at the local discrepancy of the whole rectangle R, that is going to be a sum of these discrepancies when you intersect with each grid square. And the idea is that only the grid squares intersecting the boundary of the rectangle contribute to the discrepancy. Because if you have a grid square entirely contained in the rectangle, that grid square has volume 1 over n times the volume is 1, and you have exactly 1 point in that square, as you would hope. So the contribution to the discrepancy is going to be 0 in that case, and then we don't care about grid squares which are outside the rectangle either. So really only the grid squares intersecting the boundary contribute. And for any convex set, if you have this root n by root n lattice, the boundary of the convex set is going to intersect at most roughly square root of n grid squares. So then you have basically a sum of random variables that look like this. And by a large deviation bound due to Chernoff, you can bound this above by essentially n, where the power is the constant in front. And then that was just for a particular rectangle in your class of rectangles. Obviously, there's uncountably many rectangles in the class, but the remainder of the proof lies in essentially showing that we can consider only polynomially many rectangles in the class. And the reason for that has to do with the VC dimension of the class of sets. So you may or may not be familiar with Vapnik-Chervonenkis dimension. I won't define it because it takes a long time. But the idea is that for a rectangle that picks out a particular subset of your point set, you can define equivalence classes of your set of rotated rectangles based on the subset of the point set that those rectangles pick out. And the discrepancy for rectangles in the same equivalence class is not going to differ very much. So then you have to count the equivalence classes, and that's going to be at most polynomial in n if the class of sets has finite VC dimension, which this class does. So we can consider polynomially many sets, roughly n to the 18 at most. And so if you choose a sufficiently large constant, this is going to be strictly less than 1. So that tells you that there is a realization of a point set such that for all rectangles in your class of rotated rectangles, you have local discrepancy less than this value. So this is, a standard probabilistic method argument, but I like it a lot. So just showed you here. Okay, so for the rest of the talk, I'm going to be focused on lower bounds. And I'll show you how the L2 discrepancy is exploited in this case. So remember, for the class of all rotations, that we have a lower bound of n to the 1/4. And we need this to hold for any point set, any arbitrary n point set in the unit square. Instead of studying the class of rectangles, I'm just going to simplify it to the class of arbitrarily rotated squares. A lower bound on that class will give a lower bound on the class of rotated rectangles because that's more complex. But then we have one fewer parameters. So for a rotated square, we can define that by its center, its side length, and then the angle nu that it makes with the x-axis. And we can denote a measure keeping track of the discrepancy. So here lambda is just the standard Lebesgue measure. Then you have this sum of Dirac's based on the underlying point set. Okay, so if we want to study the discrepancy of the point set with respect to a single square, so the local discrepancy with respect to that square, we can integrate over the square, we can integrate the discrepancy measure, and then extend that to an integral over the whole plane, and then rewrite things. And essentially you get this convolution between this indicator function, which this is a shorthand for the square that's centered at the origin with side length r and making angle nu with the x-axis. And then this is the discrepancy measure. And the argument now is q, the center. So if we look at the essentially L2 average of these local discrepancies over translations of a single square, so that's what this is doing, by Parseval-Plancherel, we can rewrite this as essentially the product of two Fourier transforms. And the first Fourier transform is entirely dependent on the underlying class of sets and has nothing to do with the point set. So I'm going to refer to that as the shape component sometimes. And then the mu hat, so this is dependent on the discrepancy measure, that was only dependent on the underlying point set P, because it involved the sum of Dirac's. And so this has nothing to do with the underlying class of sets, it's only dependent on P. So we've kind of separated out the information of this problem into two components, the shape component and the point component. And just as a note, if you take a particular choice of r, of side length r, so 1/2 square root of n, then you can show that there's a trivial lower bound for, oh, there should be an integral there, a trivial lower bound for the L2 average over translations, and that it's just lower bounded by some constant. The idea there is simply that in this case, the volume of the resulting rectangle is fractional. So in the definition of discrepancy, the volume part is going to be fractional. The counting part is always an integer. And so you can just lower bound that by a constant. So that's the trivial lower bound in that case. So the idea is, okay, we have this trivial lower bound. And what if we amplify this side length up to a constant? If we can do that, then we could potentially amplify this piece up to square root of n. And that's exactly what we want, because that would give, like, the square of the discrepancy is lower bounded by square root of n. And we're looking for a lower bound of n to the 1/4 for the L2 discrepancy. So the idea is that if this were to grow linearly in R, we could amplify things up. And this does not exactly hold. So linear growth of the shape component doesn't hold. This ratio oscillates wildly. And if you just look at this bird's eye view for just where nu is kind of an axis parallel, or where the Fourier transform is a Fourier transform of an axis parallel rectangle, this is what the Fourier transform looks like. So the idea is that we haven't used the fact that we're kind of averaging over rotations. And so we want to average over rotations and kind of smear the Fourier transform in this direction. We also want to smear a little bit in this direction, so average over some interval of side lengths as well. So yeah, so if you take, to fix the amplification idea, if you take an average over some interval of side lengths where capital R is just some choice of side length, and then the rotations are averaged over all possible rotations, then we have this amplification lemma for any C in Fourier space. And as part of the proof of this amplification lemma, we obtained the following decay estimate, and notice that this basically matches the Fourier decay for disks. So disks behave, or like if you were to take a square of the Fourier transform for disks, you'd get the same estimate here. And in general, in discrepancy settings, the class of rotated rectangles and the class of disks behave very similarly because of this rotational invariance property. So it's not really a surprise that you have kind of matching Fourier decay for these two classes of sets, but just wanted to mention it. Okay, and then the desired lower bound follows from the amplification lemma, essentially in the way that I said briefly earlier, where if we look at the discrepancy, we can choose this R naught to be 1/2 square root of n, and then kind of amplify the trivial lower bound up to square root of n when you amplify the side length up to a constant. So that's how that the proof goes for all rotations. Okay, so now what happens when you restrict to a restricted interval of rotations? So if we take omega to be some restricted interval rather than taking all arbitrarily rotated rectangles, what happens to the discrepancy? So this is kind of the goal of the rest of the talk, is to give a lower bound for this. And so I first was looking at this a while ago and tried to kind of just use the proof for all rotations. I thought that it would just go through in this case, but unfortunately, the amplification lemma, which I used, which I just showed for all rotations, now only holds on a sector of the plane if you restrict the interval of rotations. So if you define like an analogous sort of averaging of this shape component, and instead of averaging over all rotations, you're averaging over this restricted interval, then the amplification lemma only holds when C lives in this restricted sector based on that angle theta. And the problem here then is if we try to restrict our averaging of our L2 discrepancy, if we restrict that to averaging over or integrating over a sector, then it's unclear what's happening with this point component. Because in the previous proof for all rotations, the point component was just sort of hanging out. We didn't really need any information about it. And here, the behavior of the point component is kind of a mystery because it's entirely dependent on the underlying point set. And again, we need a lower bound for all n point sets. So it's not clear what this Fourier transform is doing or where the mass of the Fourier transform lies. That's actually kind of an interesting question, like unrelated to discrepancy. Just what is the behavior of the Fourier transform of a sum of Diracs at if you have a point set, and how does it depend on the underlying point set? Where is the mass of that Fourier transform? These are all questions that seem very difficult to answer. And so you need to know that enough of the mass of that Fourier transform lies in the sector in order to say anything about the discrepancy. But we unfortunately don't have any information about this. So the amplification idea kind of falls apart in this restricted interval case. Okay, so there's this related problem that was studied last year by Brondolini and Travaglini, and it has to do with studying the discrepancy of particular classes of convex sets with certain smoothness properties of the boundary. So if you have a convex body, the smoothness properties are measured via this, the length of this chord. So given a direction, you take the tangent or orthogonal line to that direction, move it inside the convex body by delta units, and then measure the length of the resulting chord. And for any convex set, we have kind of a lower bound of this behaves at least like delta to the power 1. And for sets with C2 boundary, such as disks, we have delta to the 1/2. So this behaves like delta to the 1/2. So their theorem says, which gives a lower bound on the discrepancy with respect to essentially dilations and translations of a convex body with certain smoothness properties. It says that essentially, if you have a convex body that behaves like an interval, or behaves like a disk on some interval. So that's what this property is saying. We need some interval where this quantity is lower bounded by delta to the 1/2, so it's really smooth on that interval. And outside of that, if you have knowledge of the correct power for that for this quantity, then we can lower bound the discrepancy of the set of dilations and translations of this convex body C by the following quantity. And so if we go back to our setting of rotated rectangles, this has some similarities now with this setting for convex sets, because we're looking at in the setting of rotated rectangles, we're looking at all translations and dilations. And we're also looking at rotations within some kind of restricted interval. So the interval of rotations you can think of as being kind of encoded in the boundary of the convex set in this setting. And so there's kind of like an analog, there's a lot of similarities between this setting and the setting of rotated rectangles where we have this restricted interval of rotations. So our lower bound, we can kind of exploit some similar techniques and get a lower bound for any restricted interval of n to the 1/5. So this is the first such lower bound for a restricted interval of rotations, but at the same time, we do kind of expect that the true lower bound should still be n to the 1/4, which would match the lower bound for all rotations. And the reason we expect that is because of those Diophantine properties that I talked about earlier. So any interval of rotations contains a number of every type. And so just based on the numerical properties of an interval of an interval, you would kind of expect the discrepancies to behave in the same way. But again, for right now, the best we can do is this n to the 1/5. And so here's our proof outline. So we have the following decay estimate for in Fourier space for C sufficiently large and inside some particular sector. And outside the sector, we have a decay estimate of C to the -4. This just holds for Fourier transforms of convex bodies in general. Okay, so the idea is that, and now I'm going to kind of transfer to the torus. So we're in discrete Fourier space now, but nothing really changes there. So if you have the sector with nice Fourier decay, so this is the sector with nice Fourier decay of C to the -3, we're going to approximate that sector by rotated rectangles. This is not to be confused with the rectangles in your class of rotated rectangles. We're in Fourier space here. And each rectangle has dimensions x, y, so length x, height y, and the area has to be roughly of the order n. And then you need this, my pencil stopped working, sorry, so I can't point, but okay. Yeah, so we're going to approximate with m rotated rectangles, where m is of the order theta times x over y. And then the idea is that if we, for lattice points in this discrete Fourier space, if we keep track of how many rectangles each lattice point lies in, then the goal is to find some uniform constant rho, depending on the number of points n in your point set, such that we have uniform control on this counting function phi. So specifically, we want rho times phi to be less than the decay estimates, so that we can essentially replace the shape component in our lower bound by this rho times phi quantity. Okay, so if you kind of split the Fourier space into different regions and count cleverly, like you have counting functions for this phi quantity, then you can kind of optimize and obtain the following orders for x, y, and rho respectively. And then basically the proof follows from there. So over here we have our square of our L2 average of the discrepancy with respect to translations, and then you're also averaging over rotations and dilations. And then again, we write this as or we split this up into the shape component and the point component, as I mentioned earlier. We can rewrite things. So this point component is going to be an exponential sum, depending on the points pj in your point set P. And then, as I mentioned, now we replace this shape component with, or the average of the shape component rather, with this rho times the phi function, which keeps track of the number of rectangles. Then we have kind of a sum over rectangles of these exponential sums based on the underlying point set P. And so now there's some lemmas of Montgomery that bound these exponential sums from below. So now we have, again, we're summing over rectangles, and these exponential sums are lower bounded by n times the area of each rectangle minus some constant times n squared. So essentially, if we basically the rectangles were of area kappa times n. So if we choose kappa large enough, then we get a lower bound of n to the 2/5 if you put everything together based on our estimates for x, y, and rho. So that was the square of the discrepancy. So then the L2 discrepancy is lower bounded by n to the 1/5. And that kind of concludes our results for restricted intervals. And again, the big question here is whether this can be improved to n to the 1/4. In the case of convex sets, so dilations and translations of convex sets, which Brondolini and Travaglini studied, they also obtain an upper bound of essentially n to the 1/5, but they have a little bit of this extra sigma. This extra parameter sigma. But yeah, in any case, they're able to obtain upper bounds, but those upper bound techniques don't seem to translate to our setting. So yeah, that basically concludes my talk. Thank you for having me.
Thanks so much, Michelle. Wonderful talk. We can take some questions now.
Let me just ask a generic question, like where do you see all this going next, Michelle?
Yeah, I'm hoping to generalize to other classes of sets, like potentially Cantor sets, done some work on that, but it seems like, yeah, you kind of run into some issues with the Fourier transform in that case, because if you use a particular like approximation to a Cantor set, the Fourier transform kicks in really far out, essentially. Because if you have a really small interval, the Fourier transform, or the Fourier decay, sorry, of c to the -3 is going to kick in really far out. So it's tough to say whether we can get anything out of that. But yeah, essentially looking at other sets and trying to get lower bounds for those.
Maybe this is already like fully known, but have people looked at discrepancy such as this for, let's say, sublevel sets of bounded degree polynomials?
I don't think so. I mean, I haven't seen anything on that, but yeah, that's an interesting thought.
Yeah, because coming from like a complexity theory standpoint, this discrepancy thing sounds a lot like what's called like pseudo-random generators and things like this. So you want some distribution that sort of looks uniform to some class of distinguishers, and these classes are like very common ones are low degree polynomials. Yeah, or I guess if you want something that looks a little bit more like rectangles, you could take like tropical varieties, something like.
Well, yeah, that's interesting. Yeah, I haven't seen anything, but maybe I'll ask around.
Maybe one other question I have is I was kind of expecting some generic way to go from, let's say, rotated rectangles to any other shape by some like mutual approximation. Like if you have some other shape, you could cut it into a bunch of little rectangles, and then if you had a rectangle, you could, pattern it with these little shapes. Is there any kind of generic reduction you can do like this to get loose bounds on other sets?
I think if there was, there'd be a lot more results already in discrepancy, but yeah, I mean, I think the issue is that like the discrepancy happens at the boundary of these sets, and so yeah, so a lot of times it depends on the smoothness properties at the boundary. So like reducing a ball to like a sum of rectangles, yeah, you don't get anything nice out of that.
I see.
Yeah.
I see. Very interesting. Thank you.
Yeah.
Okay, well, thank you so much again, Michelle, for a great talk.
Yeah, thank you for having me.